So, hello, I'm back today. Today, I want to discuss a little linear algebra. And in linear algebra, I want to discuss this topic. And this, more specifically, matrices. So, what I mean by this, I will tell first. Uh, so, the thing is, there is no such thing as, as far as I can think of, at least that is what I believe. There is no such thing as standard basis or ideal basis or true basis. There is nothing like the correct representation. It all, you might have the simplest representation, even that depends on what that the transformation is. Depending on the transformation, you might have different representations, and some of them might be more simple than the other. That is the thing, that's true. And I want to discuss how do we even at least how I see this change of basis. What I mean is, suppose you have two different spaces. So I would start. Suppose you have two different vectors. Okay, sorry. Suppose you have a vector space. You have a vector space, but you have two different ways of representing a point, you can say, in that vector space. Suppose the two different ways that the same space by two different people is represented in two different ways. And let me say that I am one of the people. Let me call M. Some guy M is there. M for me, maybe I am representing it. And there is another guy, let's say some other guy. Let me represent him by N. Some new person, some nobody, some guy. And both of us, me and him, I don't know him, maybe he doesn't know me. We are both representing the same space in different ways. This guy, whatever he measures is equally valid, and whatever this guy measures is equally valid. Now the thing is, I will measure. Of course, let me talk about myself, because I am the only one who can uh, measure according to my convenience. I have no idea what this guy is measuring. And what I found was that any point in this in the vector space I am representing, right? Any point I will in my vector space. Of course, the best way to represent is using this perpendicular axis. So basically, something like this. uh, this might be my some I cap, this might be my k cap, j cap, and I might have this k cap. And this might be even an abstract space. I might have more than one dimension. I'm not just talking about 3D or something abstract. The thing is, I have in my frame I have these numbers, right? I will have my vector space, which is spanned by these vectors. This is my first vector. This is the simplest way I can write a vector, right? There is no more simple way. I can't go more simple than this, as far as I can think of. This is the simplest way. And this guy, in this space, he will also try to be as simple as possible. Even in his space, he will also say, okay, fine, I will also use the same thing, I will also do this. He will also write like something like this, linearly independent vectors to represent a state, a position, something. Now the thing is, the biggest problem is this vector and this vector, though both of them are very happy with this, they are correctly measuring everything, they are not the same thing actually. Let me write again. This is very important as far as I can think. The vector 1 0 0 0 0 0 measured by me is in general not necessarily the same as the vector 1 0 0 0 0 0 0 measured by this guy. Why am I saying that? Suppose I have a vector space. uh, Suppose I have a vector space and I only know this point, and so, and in order to write locations I will do something like this and this, and I will nicely write a perpendicular system 1 2 3 4 1 2 3 4. I have this nice system. This is by me, but the other guy, he just knows this point and he will try to also try to be as simple as possible, but he has no reason to follow me. He might go something like this. This is perpendicular but not necessary. He can do as he like. He can also go something like this. This is also equally valid. Whatever point I am covering, he will also cover. Same. He will also cover. What I mean is, suppose I have a point which is I go something like this, but something like this, and for me this point will correspond to 2 comma who knows 1, I don't know, but this guy will argue no, for me this is just 1 0, because in just the first step itself I reached here. He is correct in his own point of view. He is correct in his own point of view, and we both will not agree with each other unless we have some kind of agreement that okay, if you do this, I will translate your language in this way. So basically we need a kind of mediator between uh, these two people. So the only way to do that is to get some information. There is no way I can know what is happening here. There is no way I can know what is happening. I have to get some information. So the information I will get, let us say, information I will get, I am the one measuring, is that whenever he says 1 0 0 0 0, okay, for simplicity, let us just keep for, let's say, 4 dimensions. You may ask, why can also have 3 dimensions, but let's just have 4, because 3 2 1 we have used, so I'm just bored of it. Suppose that I found out that whenever this guy says this, whenever this guy, in that his guy's point of view, whenever he writes this, in my point of view, like in my representation, this point is actually equal to something like this. And you can ask, if you ask like, then what is this? Well, this is linear algebra. Everything is linear. Everything just scales down. If I want to know what is this in his space, I will simply multiply this vector itself and I will get the information. And so there are 4 dimensions, and I somehow I just get all the information from his space. I need 4 vectors, and okay, I think, yeah, and again, so all of these vectors, I found out the information that okay, these vectors I can represent in my representation, in my convention, however I want. But just remember, this is no special than this, and this is no special than this. It is just two different people uh, measuring the same entity, the same quantity, however they like. But in the end, they are still measuring the same thing with just different conventions, different ways. And now, and so the thing is, doesn't matter now what what point he gives me in his space. I can always know what exactly is that point in my space. What exactly is that point, and how will I do that? Well, this thing in that guy's space. Oh, was it supposed to be n? Yeah, it was supposed to be n. Sorry. In Yeah, I wrote j everywhere because I used the alphabet j, and the reason is I learned this better by watching a video from 3 blue 1 brown, and it was he used the alphabet j, like j for Jennifer. uh, so that's how I recorded it. But now I just so much like this, and j was confusing for me. I just thought, okay, m and l, after m n comes. So now this thing, I can always write this as like this. In that guy's point of view, I can always decompose this in this way. And and since I know the relationship, what is this equal to, 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 I somehow, don't ask me how I found this relationship, that is a very different question. But once I found this, I can always convert from here to here. I can also go the reverse way. It is again just some uh, game manipulation of equations. You just send things from one to there. If you can go from here to here, you can as well go from here to here. There is nothing stopping you from doing that. And I think if I if I my subconscious mind is still with j. So if I can't give up on j, I have to use j itself. uh, uh, Let me just stick with j. Yeah, if I again use j instead of n, just we will just go with it. And now the thing is, uh, I can use a matrix representation for this. You must have heard about the column picture. Basically, if you have let's say 1 2 3 4 2 1 6 7 8, and you have some vector, we can decompose it in this way. This is called the column picture of multiplication of a vector with matrix. This was I learned this from Gilbert Strang, one of his videos. And so yeah, you can do that. And so I can actually nicely do this, right? So basically, I know what is this, I know what is this, I know what is this, I know what is this. So basically, what I'm trying to say is, I know. So let me just write it down. So there will be some matrix here which will take this 1 0 0 0 and convert this thing from here to here, and I know that this thing will be somewhere here, the vector I know, and these others won't matter for this one, but it will matter for this one. Again I will write, and again, and finally again. And all of them will have the same matrix, so I can just take the matrix out, which is sending from the other guy's space to my space, and I will just now, this is a times 1 0, and this is b times 1 0 0, and this is c times, and so on. And you can just write this now as a b c d in the other guy's space. And so basically this is a way I can how should I say, convert the point represented by him in his space into my space, and both of us are actually talking about the same thing with different numbers. So basically this is the equation to take away from here. Any vector in my space, I mean, if you have a point in vector space, I know that what that guy is how is that guy representing it, and you know, uh, there is a way to communicate. You have a matrix which takes his point and converts it for you. So this is how we connect the represent of a point between two different representations of the same thing. Remember, we are still talking about the same vector space. We are in the same vector space. It is just a different way to represent it. And now, okay, fine, we got this. Then the question will be, we can have a lot of questions, and so this is very nice, like in the, so let me not write the axis. So in this point, if I want to talk about this point, and that guy said this point, the n guy said this point is somewhat 2 times 1 0, and it has no other component. I can find out what will it be in my space. I can find out that, okay, but according to me it will be like some 3 times 1 0 plus I don't know, 2 times 0 1. So in my space, it is in his space. And now, what about transfer? What about rotation? Things like rotations, squishing, stretching, and so on. Let us see. Again remember, this matrix is still the same. I basically know the how should I say, I have the translator. I basically know how should I say, what what do I exactly know? Okay, I basically know the way to translate however is representing that same point. As I see, we both know it is the same point, but his way of representing is different than mine, and from his representation I can go to mine. I can know, okay, whatever he's talking about, what will be that in my language, and so I can communicate with him like this. This is a very important equation. And so now my next question will be, suppose I do some rotation. That guy does some rotation in his space, like he found out some rotation has happened. What I mean is, in his space, he found out that uh, his vector got rotated and gave him some other vector. And this matrix only cares about this matrix is designed in such a way that it can only work on vector in his space, his representation. It is he measured how the rotation happened, whatever happened, and so he will construct this matrix to know everything, every change happened in the space according to him. But now my question is, okay, whatever it is, even rotation happened in my way, and that guy told me that, okay, I have measured this rotation by this much amount. He gave me the information, but I have to now write it my in my representation, in my language. How will that look in my language? So in order to do that, what we can do is, so we have this, right? Now the question is, we can actually use the language of I mean, we can actually use the property of inverse of a matrix. What I mean is, if both of them if both of the representations have a complete way of representing each and every point in their space, their language is different but they are somehow representing every point in their space, there is complete, then I can have an inverse. And so, basically what I mean is, if I know if I know what point is in his space and I can translate it, he can also do the same. If I tell him what point I have in my representation, he can convert it in his representation by some other way. There is some way. So it will be like, from my representation he will go to his representation and he will use whatever information I gave him. And the thing is, this representation he used from my language to his language, this is nothing but the inverse of the previous matrix we had. This one, it is just n to m inverse. And now I can use that idea here. So what I mean is, every time uh, every time he has a point in his space, I can always decompose it in this way. Basically this will go from m to n, v of m, which can be written as t inverse of n to n, v of m. Let us use that here. So here you can see, he gave a vector in space, it got something happened to it and he got the result. And now I will try to do the same thing here. Let this Rn be as it is, I can't do anything to it. And now this thing can be written as like this. It will go from m to n, v of m is equal to, again I can do the same thing, any vector in space I can write like this, r of n. Or I can also write this as inverse of n to m v of m is equal to t of n to m r of, oh yeah, I forgot, m. And the thing is, this vector here is the effect of that rotation in my representation. Like in my representation, what will where will the point be? What will happen to that? Uh, what will happen to the representation of that point uh, in my point of view? Okay, I'm complicating it, but basically I'm telling you whatever happened in in that space, exactly same thing is happening in my space, but due to the way I am representing that space is it it might appear very different to me, even though it is the same thing. It is just a point of view. So I can write this like this now, and I can multiply t on both sides. If I multiply t this side, this will just become the identity, which is not of much use. So basically I get this equation. Now you can see that I have a point, something happened to that point, and that point got shifted somewhere else, and this quantity here is the same rotation that happened in this space, but in my representation, in my convention, in my language. So I will call this as the measure of rotation in my convention. So I will get this, and I got this nicely. So the takeaway here is, if I know, if that guy uh, did a rotation and he used this for representing that rotation, I can simply convert it into my language and write this in this way. This equation is connecting two different languages basically, but I would still like to uh, highlight on the fact that we are nothing has changed physically. It is just the way uh, we measure is different from one person to another. You can think like some person is measuring in centimeters, other guy is measuring in who knows, meter or feet, inch, anything, but at the end of the day they are talking about the same thing. And yeah, so basically on this rm you just put some vector in from your space, and it will spit out another vector wherever uh, whatever the result is. And the thing you can see here is, like when you put a vector from your space here, what this does is, so this can also be written as like this, right? First this matrix converts this into the language of n, and then according to the language of n this will rotate it, then this matrix will convert it back in our language. It's a three-step process. And this you must have seen, this is very similar to diagonalization of a matrix, which we write like this, right? Any matrix can be written something like this. I don't remember well. I think it was u d u inverse. right? So you can think in as many ways as you want. So basically, I still want to tell that my representation is no special than him and his is no special for me. The only thing special about my representation is I understand it, so it is good for me, and same for the other guy around there. And so yeah, you can think it like this, right? So basically, one guy, there is this person number one, and this is person number two, and there is this representation from so what will happen, you put any vector in the point of view of person number one, and you know that some what is the way to represent in person number two, and you so basically this what this is, first it translates from 1 to 2, and once this is happens, it happens here and it just converts back to 2 to 1. Oh yeah, I have to write here 2 to 1 as well. The reason is this is same as 1 to 2, so let me just write 2 to 1 because this is equivalent to u of 1 to 2. So here we have 1 1, and what I really want to understand the deeper meaning behind this. What is this telling? The thing about this matrix is everything is very clean, and you know that, right? Like you will just have everywhere zeros, just some non-zero value here, and then another non-zero value here, and so on. This is pretty clean. That's for sure. This is very nice and clean, and uh, and now also everything I said so far, you can kind of think it in this way. Suppose I have a space and there is just this one point over here. This point is absolute, but I have two people here. uh, Two people, let's say one guy is this one, and he nicely made his axis clean axis. So he is like he is aware like how much he can walk in this direction, how much he can, every point I can represent nicely. Suppose this guy, what I did is I initially made him blindfolded and made him spin, and just I told him walk in some random direction. He walked something like this. Then I told again walk, okay, walk again in some other direction. Maybe he walked like this. And now the thing is, he is very DC guy, but he is very sure about where to go and how to go because of this axis. And suppose I have a point here. This guy can also understand this guy can write this point, and this guy also can write this point uniquely. Both have their own ways, and even though this guy was kind of dizzy and everything, the way he represented the space is nowhere bad than him. Okay, he has some advantage, he has like maybe perpendicular, like all that, but other than that, there is nothing more special between these two guys. These two people are actually representing the same point in the same space with different notations, with different conventions. And all this formalism is just a way to translate from one convention to another convention. No physics is going on anywhere behind the scenes. It is just a translation. A translation, I don't mean the movement, I don't mean displacement, not that translation, language translation. And the reason why diagonalization I think good is, suppose I will just take a 3 by 3 matrix case. Suppose this is I diagonalize the matrix and I got something like this. And you know what this geometrically means, right? It's very good thing, like it's a very good thing. You have some axis, let's keep everything perpendicular. The x-axis just got stretched by 3 times, y-axis just got stretched by 2 times, z-axis got stretched by 4 times, and that's it. That's pretty much it. Why this is useful is in the other space something else, something even crazier happening. Who knows? This thing you completely got something like it got transformed into this something, and it got the y-axis got transformed something like this and this. It might be very weird, but you can just get out of all the complexity from this. So basically, the reason is instead of using this, you can use this, and still you will lose no information. Everything about the space you do know, because as long as all the information is inside this, all the information is encoded inside this, you don't need this more than just translating the point so that you can use this ultimate thing. This is very nice. So basically all you have to do is just change the matrix. You get a new, you just use a new matrix such that in that new coordinates you just do this matrix u, and so whatever matrix you give in that coordinate, you can always first of all just convert it from that to that old coordinate, and this guy will do the job. Okay, I have to write numbers. I'm using subscripts will confuse. So yeah, in that other new representation, all you have to do is this will just convert first to the older one, and this thing can only work on the older one, and it will just do the same, uh, and it will just spit back the to the new representation, and this is same as u of 1 comma 2 1 to 2 inverse. And pretty much that's it. Uh, that's all that happens. That's all the use is. You just use this for convenience. You just do this once, just change the basis, and you will never need to use this again, other than just using it as a main source of getting the information from the points. Once you get the points from this m, you just convert that point into a more simple way that you please. That's why diagonalization is I think very useful, because you can you know arbitrary basis, you can just make all of them perpendicular to each other. That's for sure. Your work is reduced now. This is nothing. Your all that all those like squishes, like initially all that squishing of a cube, squishing, stretching, everything, there is all that squishing and rotating whatever just got converted to stretching. Everything is either stretched or compressed now, but there is no squishing, or there is no squishing, no rotating, nothing. It is just extensions or compressions. uh, your work got reduced, and I think that is a good thing in itself, right? And I really want to discuss about block diagonalization, but maybe some other day. I want to study this in point of quantum mechanics, but mostly I am trying to keep things as general as possible in pure math point of view, because it just feels good. I mean, this whatever physics there is, whatever quantum mechanics, whatever crazy stuff there are, linear algebra just doesn't care. Math is still math. You can just use it anywhere in the world, whatever you want to do with it. It is just so general and abstract. It will just work as long as you have measured things right, and you know what you are doing. As long as whatever representation, whatever things you are using to measure, you have every point covered. Well, that's all for now. I don't want to bore you more, and I don't even know if anybody will watch this, and I am not even doing for that. But yeah, thank you. Bye.